Okay. So thank you very much, first off. And I work at Intel, which means that legal matters, and so sorry for all the disclaimers. What I want to talk to you about today a little bit is the transformation that we see that's being enabled by new special purpose hardware that's coming out that allows for trusted execution in it. So just to set a little context for the value and that trusted execution can bring to blockchain applications, let's go back and just sort of synchronize on a little bit of what it means to be part of a blockchain right now. So really, blockchain at its core is this fundamental move from trust in institutions to trust in community that is facilitated by blockchain technology. It's a move from external organizational trust to communities that come to some kind of agreement about what truth is and then act on that truth. So when we talk about blockchain, obviously it's this fancy data structure. We hear all about things like Merkle chains and Merkle trees and cryptography and all of those things. But really, as far as we're concerned from the value that it brings to us, the blockchain first and foremost is an immutable record. It allows us to establish an agreement about a history very, very efficiently, and we know that that history is the same that we're considering. That history then is ordered, and by some definition of correct, is correct. So what we know is that a set of basic principles for what is accepted, what is a valid transaction, what is a valid record in the log, have been committed in that immutable record that we have. This record is determined by a community. Again, it's not someone on high saying that this is truth. It's all of us collectively providing our vote into what that truth is. And really, the core technology principle underlying this is that we achieve this agreement through some notion of redundant computation. And so what I mean by that is we have gone from sort of centralized databases, where the host of the database is the one that you essentially trust for determining truth. So a transaction goes into the database if the institution that's hosting that database has set up a set of rules, and they have administered that rules, and we trust them to manage the data appropriately. In this new community-based space, we replace that with lots of instances of that computation. So rather than having a single database that manages the transactions, we have lots of copies of the database that manage the transactions. And as long as all of those databases, as long as all of those copies of the database agree, then we all agree that this is some variant of truth. And that process of coming to agreement is what we call consensus. So the core underlying principle behind what we've been doing with this transformation from institutional trust to community trust is replacing our old notions of centralized compute with a new notion of redundant decentralized computation. Now, there are certain implications for that. Number one, the basic principle of redundancy is that we are giving up efficiency for the sake of resiliency. So we're using a whole bunch of extra computation in order to make it trustworthy. But that computation is not giving us more transactions or more throughput or more complex interactions or more complex computation. What it's really doing is just giving us more resiliency. Second thing is that it's not really performant. At the core of every blockchain, and we can have this conversation later, at the core of every blockchain is this notion that we all come to agreement on a total ordering of transactions. That is this immutable record that we talk about all the time. That core agreement means that communication has to flow among all of the participants about what that ordering is. And that consensus process, the agreement process, is fundamentally not performant. It becomes a single bottleneck around which all of our computation takes place. Blockchains in general are not scalable, and what I mean by scalable is one of those really horrible words that can mean anything you want it to mean. What I'm really looking for is, if I add more resources, do I get more transactions? And the answer in the blockchain space is generally no. because that ordering becomes the bottleneck that keeps us from being able to add more computation to it. So if I add more computation to Bitcoin, what I get is more resiliency to attacks, but I don't get more transactions per second. And the final thing is that because of these notions of redundancy, if we want agreement on correctness, then everyone who's participating in that redundant vote has to have all of the information about all of the transactions, which means, and we talk about this all the time, blockchains are transparent. They open up the doors for confidentiality. And yes, there are some techniques that we're using out of the cryptographic space for zero-knowledge proofs and homomorphic encryption and other things like that that allow us to get some level of confidentiality. We're still doing some ability to partition ordering from computation and some of the newer off-chain computation models, but still we have to have that redundancy, and anyone who's participating in the vote still has to be able to see the information in order to determine correctness. So what we're proposing really is a fundamental paradigm shift from redundancy as the basis of trust to hardware-based trust using trusted execution environments. So what we get is by delegating trust to our computational platform is we get the ability to have decentralized applications and still have verifiable compute, verifiable results as a result of that, without having the kind of redundancy and all of the characteristics that go with that. So, for those of you who aren't aware, there's a new class of computational capabilities called trusted execution environments. And I say new because, well, they've been around in some form for quite a while at different levels. So we've seen HSMs for storing secrets. We have the MEs and CSME and a variety of trusted boot environments that give us some level of restricted trusted execution. But more recently, we have encrypted memory capabilities like the SEV capabilities from AMD and the MKTME from Intel. We have more general purpose trusted execution environments that are becoming available as well, from TrustZone from ARM, SGX from Intel, that's the software guard extensions from Intel. And there's a really new, exciting open source one for the academic research community called Keystone, and I believe Don next door is talking a little bit about that, so I would suggest finding Don Sung on that. What is trusted execution? Trusted execution is hardware support at some level for a variety of characteristics, which include the ability to protect sensitive information. So the memory controller encrypts memory as it comes into the processor, or sorry, decrypts memory as it comes into the processor and encrypts it as it leaves the processor. So read and write operations on physical memory are done through a memory controller that manages encryption. So all of your main memory becomes encrypted at some level. This allows us to protect both the instructions that are being executed and the information or data that's associated with that computation. TEEs also allow you to do measurement of the computation that's being performed. So that means that we can attest to the characteristics of the execution. And through a third-party or cryptographic record for the attestation, we can prove to others outside the platform what actually took place inside the platform. So it's hardware support for protecting the application and the data from, I'll say, depending on the hardware, depending on the TEE implementation from the host, but clearly from anybody else who's executing on the platform that way. So what that means for blockchain, there are three properties of the TEE that we really look at. Number one is confidentiality. So the host, even the owner of the hardware, does not have the ability to look at the information that's being computed inside the trusted execution environment. Second property that's important is integrity. That is, the execution, the application was executing, the code that was executing, is guaranteed to be the one that we expected to be executed. And then the third-party attestation allows us to reflect that computation that took place to others outside the platform. So the way we use that for decentralized computing and things like blockchain is that we take that computation, we perform it in a trusted execution environment, and then we prove to others that the computation took place and generated a particular output. So I can use the fact that I know what was executed, I know what information was provided into the trusted execution environment, and I know what was generated, and so I can sign that transaction in a way that others can verify that that computation took place. So what that means is you can execute something on your host, give me the answer, and I know that you did not tamper with it and did not corrupt that computation. And that's really the critical characteristic that we use out of the TEE for doing these blockchain applications. All right, so I'm going to talk about two areas in which our research group has been using trusted execution in order to make improvements in blockchain technology. First is around consensus, and the second is around smart contracts. So we'll start with consensus. Let's back up for a second. So we're all familiar with blockchain, or with Bitcoin and proof of work and hashing and all the wonderful characteristics that go along with it. Proof of work is really about two things. There's Sybil protection, and we'll talk about that offline separately. But it's Sybil protection and leader election. So the core in the leader election is we want, in a fair way, to come up with a leader who's going to propose the next block that's added to the chain. And we want to do it in a way that is easy for others to verify correctly, that way. So the basic idea of leader election in Bitcoin with proof of work is that we guess some random variable, we hash that random string, including the block that we're proposing, and if the number that comes out of that hashing algorithm is small enough, where the difficulty allows us to adjust the commit times, if it's small enough, then that random number that we generated becomes our proof that we did the computation correctly. And we just keep going and continuing to guess over and over and over again how that works. So it has some really nice characteristics. As a computer scientist, right, this is really cool stuff. What it allows us to do is to have fully decentralized leader election. It allows us to easily prove the correct execution because I can just take that nonce and run the hash and verify that it matches the difficulty level. It's completely fair. Anybody can be elected leader, which means that we get all of the censorship resistance that we want out of it. It also allows us to do some really nice things from a protocol perspective. That means that we can do order n, or basically the amount of computations required is proportional to the number of validators who are in the network, rather than the square of the number of validators in the network, which is what the traditional Byzantine fault-tolerant algorithms provided for us. Problem with proof of work is that it really uses an awful lot of power in order to accomplish its job. So we were looking at this several years ago, trying to figure out if there was any way that we could make some improvements on this. And one of the characteristics that we noticed is it's not really the proof of work that's critical for the protocol. What's really critical for the protocol, what makes the protocol scalable, is this random interval that it takes in order to find the leader. All right? So when you look at leader election and look at block publication in Bitcoin, what you'll see is that the blocks arrive at random intervals. That random interval is exponentially distributed, which has, again, some nice characteristics for it. And that distribution is really the core to the protocol. Right? So the reason why I get order n messages in the protocol, the reason why I can scale this out to thousands of validators, is because of this characteristic of random arrival of leader election. All right? So if we want to make some improvements to it, we don't necessarily have to do the hashing. It's not the hashing that's really important. It's the fact that the hashing gives us really a distributed random number generator, right? So the amount of time that it takes me to find a nonce that meets the characteristics is random with an exponential distribution, all right? That's the critical observation. So if I want to replace proof of work with something more efficient based on trusted execution environments, what I really need to do is to just do a fair random number generator. And guess what? Rather than doing repeated computations over and over and over again on these hashing functions, all I really need to do is to call a random number generator. We've got hardware support for that. That takes, a few thousand cycles rather than a few terawatts of power to find that random number. It's a really easy computation that could be performed. So the basic idea for the TEE execution that allows us to get some of the characteristics of the Nakamoto consensus that's in Bitcoin is you generate a random number, you wait that amount of time that the random number that suggests for you. If you haven't seen a block during your wait, when your timer expires, you claim to be the leader and you go. So we're replacing those exponentially arriving blocks with really just a random number, where the TEE can attest to the fact that the computation of the random number was correct. And that's really the critical part for the trusted execution environment. The hardware attests to the fact that it generated a real random number and that you waited that duration for claiming the leadership on it. So what we end up with is fully decentralized. Every validator in the system can run their own random number generator. It's easy to prove that it was correct. We just have to check the signature from the enclave on the claim that it waited. So instead of checking the nonce, we're just checking the signature of the enclave. It's completely fair. Anybody can be elected leader in the same way, because whoever generates the smallest random number is the one that's going to be elected leader, which is pretty much the same thing we got from proof of work that way. The real benefit here is that there's very, very, very little computation that's required. So you basically generate a random number, and then you sit idle for a certain amount of time, waiting for that timer to expire. And so what we end up with when we're comparing proof of work with the proof of elapsed time is that we all have transaction validation costs. We all have kind of communication. There's no differences in our fundamental characteristics that way. But what we're really doing is replacing hashing with a cost of TE entry and exit and the computation of a random number. You can go back and look at a number of sources, and you'll see that Bitcoin right now is using terawatt hours per year. I think the lowest number that I could find was about 40 terawatt hours per year. Assuming 500,000 servers executing the POET, which gives you resiliency that's roughly corresponding to what the current proof of work gives you, you're talking about a few gigawatts of power per year in order to do the consensus this way. So what the TEE gives us is a way of reproducing the fundamental characteristics of proof of work without any of the overhead that goes along with it. Oh, by the way, the punchline is coming in a bit. Hold off. So the second part of this is the smart contracts thing. And we built this technology called private data objects. It's available through Hyperledger Labs. If anyone's interested, talk to me afterwards. But really, it's about confidentiality, efficiency, and scalability on contract execution that way. So again, sort of, this is blockchain 101 at some level. Is what a smart contract is really a replacement of a simple deterministic transaction with the execution of some code. So what we're really doing is replacing ordering of transactions with an ordering of messages or computational invocations. And associated with that is some potentially complex behavior that goes along with it. So the code represents an agreement between us. Transactions are simply requests to invoke some method out of that agreement for a state change. And then the blockchain is responsible for just ordering these requests or these invocations that way. And I will not go through the example that goes with this. I'm sure all of you have your favorite smart contract examples. So again, let's go back and talk about how it really works today. All right? So in the past, if we wanted to have triggered database actions, we had a single service that ran our databases. We go to Oracle, we go to IBM, we buy a database, it has triggered actions, and these roughly correspond to the things that are smart contracts. Or if I want something that's even more complex, I build a web server with a bunch of interfaces to it and APIs, and I do the invocation for it. We all know how that works. Problem with that in a single organization is that I'm trusting a single organization to do that. So what we've done in order to make this work in a decentralized environment is basically run that computation multiple places and then vote on the answer that comes out of it. So just to give you a rough idea, in Ethereum today, there's between 20,000 and 25,000 validators. So when you do your CryptoKitty operation, in order to create your genetically unique, cryptographically genetically unique CryptoKitty, you're using 20 to 25,000 servers worth of computation in order to do that. This strikes me as a problem, but okay. So in this model of doing sort of on-chain execution of contracts, every validator executes every update on every transaction. The validators have to agree. That takes time. It takes communication for it. And furthermore, in order to actually perform that computation and verify the results, everybody has to have every contract in order to do that. So doing things confidentially is really a challenge in that environment. So we end up with the current implementation is not confidential, it's public. It tends to be inefficient in the sense that, yes, for decentralization, I want some redundancy, but do I really need 25,000 servers worth of redundancy for a CryptoKitty operation? Maybe, right? Maybe. That's kind of up to you. And it tends to be because of the agreement that's required on it tends to be relatively slow, talking about tens to hundreds of transactions per second on it. So on trusted execution, basically what we're suggesting is that we move that computation into the TEE, and then we execute that one time, and I'll say one time, inside the TEE. The TEE produces a proof of correctness, and then we order the proofs of correctness rather than the executions. So the other validators verify the proof and accept the update. So again, we're back in the situation where contract execution can happen independently of ordering, which allows us to add more computation and more complexity in the contracts. Because the characteristics of the TE, the execution of that contract is private, right? Remember, even the host can't look in and see what's happening. It can be done efficiently in the sense that we only need 1 or 2 copies of it in order to establish its veracity. And it can be scalable in the sense that if I add more computation, I can get more complex transactions or more complex contracts and more of them in time. So we did this thing called private data objects, as I mentioned before. This is a Hyperledger Labs project right now. A private data object is just code and data that's associated with it. The code defines the access and update policies on the data. Data is encrypted as long as it's outside the TEE, and that includes encrypted from the owner of the data, which allows us to do some really nice sort of collaborative computations where even those who own the data don't have the right to change it that way. So the data can only be decrypted inside the trusted execution environment and the computation that happens there. So we get correctness of the contract execution from the TEE. It computes essentially a state transition on the contract. So there was something that came in, a particular invocation on that state, and a new state was generated. We take the hash of the input, the hash of the invocation, and the hash of the output, and that's what we actually push into the blockchain for ordering in order to get consistency in the ordering on it. So the blockchain just verifies a proof of correctness, serializes the state transactions that way. So what we get out of trusted execution for smart contracts in this case is that the contract state can be committed by a single TEE. And I will say we continue to use extras to do verification on it. So we have a very optimistic execution. We commit on a single TEE's claim. We do allow revocation on multiple just in case something went wrong, and I'll talk about that in a second. Correctness, and really this is the critical point. Correctness is decoupled from ordering, which means that we can throw as much resource as we want into the contract execution independently of the ordering. So we're still restricted by the limitations of blockchain for ordering, but the contract execution itself can be as complex as we want and can be as scalable as we want. And the critical thing for most of the enterprise customers that we're talking to right now is that it preserves the confidentiality of the computation completely. So, based on these examples, my claim is that that these trust execution environments become a game changer for blockchain applications. They allow us to do cost-efficient computation. We don't need the tens of thousands of redundant environments. We can do it with relatively simple TEE-based computations. It's performant, it's scalable, we can add more computation and get more complex and more transactions, and it does the confidentiality preservations for it. These are all really good things, right? So if we stop now, I would say, hey, look, if you believe that the TEEs work perfectly in the way that we talk about it, well, guess what? We don't really need homomorphic encryption anymore because we can just do the computation inside the execution, the TEE. We don't really need zero-knowledge proofs anymore because everything we get from the zero-knowledge proofs we can just do in the TEE. That would be lovely. However, attacks happen, right? So, and by the way, this is absolutely true no matter what technology, whether you're talking about cryptographic technologies or TEEs, attacks happen and we have to accommodate those attacks. And just kind of going back and looking at the examples we've seen, like the effective Ethereum Classic and the 51% attack that took place, apparently took place last weekend on it. That's no different from the TEEs, from the trusted execution environments. The attacks happen. So we really have kind of two choices here, right? One is to believe that the TEE works the way it's supposed to work, and this is lovely and wonderful, and there's some utopian environment in which we can just do this great performant execution. And the other is it doesn't work, so we just throw it out because it's not perfect. Our argument is really that we're someplace in the middle there, that this is part of building a secure system. And let me just go back and talk about what the potential is here. So if an adversary can compromise execution of an enclave, what could they do? Well, since the core of the enclave computation in POET is leader election, it means that they can be elected leader whenever they want, and any adversary that can be elected leader at any point in time has complete censorship power. And that's really what it comes down to, that way. In some cases, that approach becomes sort of worst case security architecture, in that if you compromise one enclave, you've essentially compromised the liveness of the entire system that way. That's bad. So the approach that we took in order to do this was to basically come back and throttle actors on it. So in Bitcoin, anyone can win any block. It would be possible for a miner to win 50 blocks in a row. It would be possible. It's not likely to happen anytime soon because the probability is extremely low. And so what we basically said was, look, there's a point at which we can say, no, the probability of that happening is so low that clearly if it happened, it's more likely the cause of an attack than it was as a result of somebody getting really lucky. So the approach that we took in this case was to basically say, hey, we'll go to a 95% confidence interval. Anything outside that 95% confidence interval, we're just not going to allow you to be elected leader this time around. And what that means is a well-behaved actor that's executing the protocol, when they realize that if they were elected leader the next time, they would fall outside the 95% confidence interval, they just don't play this time, right? They just sit it out. But that also means that any bad actor also has to sit out. So what we've done by adding this confidence interval is put a throttle on bad actors that they simply cannot win every single block. And so when we've run just the experiments that we have, even with a third of the population as compromised, doing the worst possible behavior that they are allowed to do, we still end up with something in the order of 50 to 60% of the blocks being published by good actors. So what that really means is the performance has been affected because, at least from the censorship side of things, it may take you a little longer to get your transaction committed, but your transaction will be committed. So we have correctness and we have liveness in that any transaction that might be committed will be committed eventually. So the throttle acts as a circuit breaker in this case. And what this means is that POET is not really a replacement for proof of work. Right? It's not something you're going to do in a public cryptocurrency. However, in many of the enterprise applications where you have extrinsic motivation or incentives for participating, it's a really good, really lightweight consensus algorithm for it. So, kind of stepping back then, when things work with the TEE, it's really good. Compromising these hardware-based trusted execution environments is very difficult, and if I take care about how I deploy them, that is, the environment in which I place them, I can make it really, really hard for any compromise to take place. So that allows us to be optimistic. We assume it works, design our protocol around that optimistic assumption, and then put throttles or circuit breakers in. Second principle is we make sure that there's no big targets. There can't be any single key that can be compromised that would allow you to compromise the system. And again, deployment is a fundamental part of the solution. That is, your TEE is situated inside a bigger security system. And in that bigger security system, you can make certain guarantees about the complexity of compromise versus the value of the transactions. And that allows you to do these really nice, optimistic decisions for execution that way. So, in summary, then, trusted execution can be a real game changer for blockchain applications. It allows us to do some really, really, really nice things with designing protocols under certain assumptions and with some certain characteristics in the protocols. Now, I laugh. The original POET, or proof of elapsed time, consensus algorithm, it took us about a week to come up with the algorithm based on the assumption that the TEE was perfect, and it took us about 9 months to come up with all of the circuit breaker ideas that we have in order to protect it against that. So, the optimistic design is easy. The design to make sure that you haven't created vulnerabilities is much harder, and that's really where it is. So, trusted execution is great. It's not a panacea. It's not going to solve all of your problems. Finding the place to use it is really the critical part. And really, most importantly, in all of the examples that we have in the protocols we're developing, what it allows us to do is to start optimistic and then create fallbacks and circuit breakers, which means that under normal circumstances, we get fantastic performance characteristics, and then we fall back onto these other environments. All right. That's all I have for today. Thank you.